really comes back to the user space. So this is what, as I think I have already explained it in my earlier classes also, because so this is what you call it as context switching. When the CPU switches from the user space, that is, as long as the CPU is executing the user program, we say it is in the user space, because it is performing the execution of some piece of code which is there present at the user address space of the memory, which contains only the user programs. When that user program, within that user program, if there is a call made to some system call which is residing inside the kernel address space, then the CPU will switch from the user mode execution to the kernel mode execution. So this time, the time taken by the CPU to switch from the user mode execution to the kernel mode execution, we call it as context switching time. So and usually this context switching time is high than compared to calling a function within the same program. Say for example, I have written a program, and in that program, I call a function which is again residing in the user address space itself. So that calling is much faster than compared to the CPU switching from the user address space to the kernel address space, because there is totally the change of what the address space itself. So now the process is entering into the memory space where the kernel is residing, and since I say it's the kernel, the core part of the operating system, so it is in a protected environment, and when the CPU enters into that environment, it is not possible for any other process to disturb it until it voluntarily comes back to the user space. So now we have kernel, you understood, that's the core part of the operating system. And again, kernel, you can have two types. One is monolithic kernel and another one is microkernel. So these are the two different approaches which are adopted for building the kernel of the operating system. Now, what is monolithic kernel? Monolithic means a heavy kernel, the kernel which is large in size and which has a lot of kernel modules present in the same memory space under the single kernel thread, something like this. A monolithic kernel with all the operating system services in a kernel space. So that means, so monolithic kernel is something like heavy, bulkier, and it has all the services in it. Now, what is the drawback with this? What is the drawback with having making the kernel bulkier by having all the services in it? So the major drawback is that if some kernel module fails, so then there is the possibility of the entire kernel failing. So this is one drawback, because since you have made the entire kernel as bulkier, if one of the module inside the kernel fails for some reason, so it will definitely affect the all other modules of the kernel, and the entire kernel will be down. Now microkernel is something like microkernel is making the kernel very light, or keeping it as much as small as possible. That is what is microkernel. So name micro itself says the size of the kernel is very low. Now how do we make the kernel light in weight? So by incorporating only the essential set of operating services into the kernel. So don't go for putting all the services into the kernel. So go for putting only the most essential services into the kernel. So this way you can make the kernel much lighter, and this way the kernel can also run much faster. And what is that you're going to do for the other non-essential services? Now other non-essential services can be implemented as servers which run in the user address space. So we don't have the other non-essential services running at the kernel address space. Now we have them implemented as servers, and they are running at the user address space. When I say they are running at the user address space, so the user program has easier access to them even without the context switching, which I mentioned in the previous slide. So the user programs can easily access those things. What are those non-essential services? So these are the example for the essential services: memory management, timer system, interrupt handlers. All these things are the essential services, and the non-essential services are implemented as the separate servers, and these servers, they will be running at the user address space itself. And so say what kind of servers, if you ask me, so they are something called as the web server softwares, Apache Tomcat, Apache Kernel, all these things, you can install them as a separate package, and we don't have those things running at the kernel of the operating system. They will be instead running at the user address space as user applications. So the benefits of the microkernel model are the robustness. So if the problem is encountered in any of the service which runs as a server, can be reconfigured and restarted without affecting the entire operating system. Configurability is also another important advantage of the microkernel, because you can easily configure the server applications which are running at the user address space without need for restarting the entire kernel or the entire system. Now, types of operating system. So there are two types of operating system. One is general purpose operating system, another one is the real-time operating system. Now, and the general purpose operating system is generally used in the systems which are non-deterministic in behavior. That means that the general purpose systems which perform a lot of functionalities, hence we say non-deterministic in behavior, because they can exhibit different kinds of behavior. When I say the embedded system, they are deterministic in behavior because they exhibit only a fixed set of functions, and you know what it performs. But general purpose operating system or the general purpose computer system can be used to perform any type of computation and functionality. That is the reason we say it is non-deterministic in behavior. Examples for the general purpose operating systems are these many, which you already aware of: Windows 10, Windows 8.1 or XP, MS-DOS, Windows 7, etc. Now, real-time operating system, as already told, is deterministic in nature, used in the systems which are deterministic. That deterministic is nothing but, so they perform fixed set of functions. Since they perform fixed set of functions, so their behavior is well known, we say it is deterministic. RTOS services consumes only a known and expected amount of time regardless of the number of services. RTOS decides which application to be run, should be run in which order, and how much time needs to be allocated for each application. So this is what the real-time operating system does. It decides which application to be run and how much amount of time the application has to be done, all these things. Examples are Windows Embedded Compact real-time operating system, QNX real-time operating system, and many more are there. Now, real-time operating system also has kernel, so that is called as real-time kernel. So just as we discussed in the previous slides, so any general purpose operating system has something called as kernel. So similarly, the real-time operating system also has the core part called as real-time kernel. Now, what are the main tasks that are performed by the real-time kernel? And again, here also the real-time kernel only minimal set of services are kept inside it. So, and what are the basic functions that are present inside the real-time kernel? So, as we already discussed, process management, process scheduling, or you can also call it as a task, process synchronization, exception handling, memory management, interrupt handling, and time management. So these are all the things which we understood earlier also. You'll find the majority of these things even in the kernel, real-time kernel also. Now, what is the process management? So process management, as already highlighted a few points with respect to the process management, that is it's responsible for allocating the memory space for the process which is ready to execute, and also responsible for allocating the necessary resources, all these things. Now here also within the real-time kernel there is something called as process management, which is responsible for allocating the memory space, loading the task into the memory space, allocating the resources, and setting up the task control block. There I told process control block, PCB. Here it is called as task control block. So, or you can, if you want, you can also call it as the process control block also, not a problem. So, and this is the data structure which is used in order to store all the intermediate results of the process when the CPU is about to switch from one to the other. Now the task control block is for holding the information corresponding to the task. And what are the fields that are present inside the task control block or the process control block? One is the task ID. So, or you can also call it as process ID, because every process is uniquely identified by using a number called as process identification number. So that you can also call it as the task ID. So there inside the task control block data structure or process control blocks data structure, there is a field which holds the identification number of the process, or the process ID in short form, or the task identification number. And other thing, the second field is the task state. Now it saves the current state of the task, what state it was, whether it was in the ready state, whether it was in the block state, whether it was in the execute state, all this thing. That current state of the process gets saved into the state, task state. And then the task type, it indicates whether the task is of hard real-time task or soft real-time task, or whether it is just a background running task. So, and then task priority also. So this stores the priority of the task. That is a numerical value which tells the priority of the task, and this priority information will be used by the scheduler for scheduling them for execution or assigning the task the CPU for execution. So if this field carries a highest priority number, then it is given the first preference for execution. And then task context pointer, a pointer of the context saving, context pointer. It points to the current context of the process or the task. Memory pointers are also there, which points to the code memory, data memory, stack memory of the task. So every process of the task which is executing will be having these things. One is the code memory, which is holding the instruction; data memory, which holds the data related to that particular task or the process. And at the same time, there will be something called a stack memory also, which will be used by the processes or the task to store the return addresses. Whenever they make a call to the function, the return address gets saved onto this. And similarly, system resources pointer, because when the process is executing, so it will be using many resources. The resources could be the semaphores. Semaphores is basically used for synchronizing the processes when multiple processes are using the shared resources, common resource. And similarly, there is something called as mutex, mutual exclusion. Mutex means mutual exclusion. That means when there is a shared resource and multiple processes are competing for using that resource, so you got to provide the mutual exclusion. That means when one process is using that resource, it should not be possible for any other process to use that resource until the process which is currently using the resource releases it. So that is called as mutual exclusion. Now task pointers are also there, are the process pointers. That is one PCB or one TCB pointing to the next PCB or the TCB. So it's something like the singly linked list, where this field, the task pointer field of one TCB, is just pointing to the another TCB. So this. Now using this, you can create a chain of TCBs or the PCBs. So these are the fields of the task control block or the process control block. Next, process scheduling, how the process gets scheduled for execution. So kernel has something called as scheduler. So this is the one which is responsible for deciding which process should be allocated the CPU for execution. So there can be a number of processes ready for execution, and CPU is the only one which is present. Now the scheduler makes the decision which process should be allocated the CPU to execute next. So this is again an algorithm implementation. So there are many different types of schedulers. First come first based scheduler, priority based scheduler, round robin scheduler, shortest job first scheduler. Many things are there, So and I hope we are going to discuss all these things in at the later point of time. So now the process scheduling is performed by an application which is called a scheduler and which is present inside the kernel. And then the process synchronization, and again when I say multiple processors are executing on the system and concurrently they want to access the shared resources, then you got to provide the synchronized access to the shared resources. Now you cannot allow 2 or more processes to simultaneously access the resource. When one process is accessing the shared resource, you should prevent all other processes from accessing that resource until the resource is released by the process. Now once it is released by the process which was holding it currently, so next the process management component which is there inside the kernel will decide to which next process the shared resource should be allocated. Now exception handling and is error control is another important service that is offered by the kernel of the operating system. Now this exception handling deals with many of the exceptions or the error handlings that arise during the execution of the task. So to name few, insufficient memory, say you're trying to run a program but there is no sufficient memory present inside the system, that time the exception will be raised. Timeouts, deadlocks, so this can also occur if 2 or more processors, if each of them holding some resource and competing for the resource which is currently held by the other process, and ultimately if none of the processes wants to release their resources and waiting indefinitely to get the resource which is currently held by the other process, so what will happen? This situation we call it as a deadlock. So it means none of the process, each of the process is holding some kind of resource and they are not ready to release the resource, and they still require the resource which is currently held by the other process, and now none of the process can execute and the system continues to be in the same state without any operation or without any work being actually done. So that situation we call it as a deadlock situation. And then many other bus errors, divide by zero, unknown instruction execution or illegal instruction execution, all these things. And then exception can happen at the kernel level service or the task level. So deadlock is the best example for the exception that happens at the kernel level service, because all the resources, as I already told, it is maintained and monitored by the kernel of the operating system. So if the deadlock happens, it is something related to the kernel related service. Even in spite of the operating system kernel doing all this managing of the resources, so there is a deadlock. And timeout is a task level exception. Now deadlock, the explanation is given here, is a situation where the set of processes are blocked because each process is holding a resource and waiting for the another resource acquired by some other process, and if the same process continues, so we say it is in the deadlock situation. So that time again the kernel will intervene and it will forcibly try to get the resources, some of the resources which are currently being held by the lowest priority process, and it will allocate them to the highest priority process. The moment the highest priority process gets all the necessary resources and it finishes its task, all the resources will be released back to the system, and then the kernel will go for allocating them to the lowest priority process. And similarly, timeouts are the best example for the exceptions that happens at the task level or the user level. So if no response is received after exhausting the limit, the feature may be aborted. So this is say I have written an application and it is executing, and I want some response to be received within some stipulated time period. If the response is not received within that stipulated time period, I say that feature is aborted or that feature is discarded, something like that. Now memory management unit, again within the RTOS also you have something called as memory management unit. And this memory management here is implemented, generally uses the block based memory allocation technique. So RTOS generally uses the block-based memory management technique instead of the usual dynamic memory allocation technique used by the general purpose operating system. So GPOS uses the dynamic memory allocation, whereas the RTOS uses the block-based memory allocation technique, because block-based memory allocation techniques are much faster than compared to the dynamic memory allocation, and that is block-based is necessary in RTOS because we are saying them as a real-time operating system. They should function in the real time, and the delays are not supported. And the quickness is required, and that quickness can be achieved by using the block-based memory allocation technique rather than the dynamic memory allocation technique. Usually the dynamic memory allocation techniques, they take much time for allocating the memory. So RTOS kernel allows tasks to access any of the memory blocks without memory protection to achieve the predictable timing. Again, general purpose operating system, we understood that there is something called as memory protection system as well present inside the kernel, but inside the RTOS kernel you don't find any memory protection system. Why? Again, this is nothing. Again, when I say protection, again it is for the additional overhead. It increases the burden on the system, and if more the burden, then you cannot achieve the things in the real time. Since RTOS is main purpose is to do the things in the real time, again we have the protection system also avoided in the RTOS. And some commercial RTOS kernel allows the memory protection, but it is not mandatory, it is optional. And the kernel, say something happens, now we are saying the memory protection, so the protection system is optional for the RTOS kernel. What will happen if there is the protection violation? If something unusual happens, then the kernel always enters into a mode called as fail safe mode. So that means it enters into the fail safe mode and prevents all other damages. So this is the simple thing what the RTOS employs. Now interrupt handling, this I already told. Interrupt is interrupt is used generally to draw the immediate attention of the processor, because CPU will be busy doing its own task. If you want to make the CPU perform something else, you got to draw the attention of the CPU, and attention of the CPU can be drawn by generating the interrupts. And interrupts, again, there can be two types: synchronous interrupts and asynchronous interrupts. So the interrupts which are usually generated by the software fall under the category synchronous interrupts. Say for example, divide by zero, memory segmentation errors are the example for the synchronous interrupts. So why they are synchronous interrupts? Because the interrupt handler for all these things, they run within the context of the same interrupting task. Now, whereas in asynchronous interrupts, examples are this: timer overflow interrupt, serial data reception, transmission interrupt. So example for the asynchronous interrupts. For asynchronous interrupts, the kernel handler is usually written as a separate task and runs in the different context. Hence, the context switching is required. Now, all these things, it happens within the same context, and the CPU need not change the address space from the user mode execution to the kernel mode execution. Whereas in asynchronous interrupts, there is a need for the CPU to change switch from the user address space to the kernel address space. So context switch is happening here, and hence we say handling the asynchronous interrupts are much lower than compared to handling the synchronous interrupts. So time management, this is again necessary, and even in RTC, this component has to be there, because RTOS, this component has to be there because real-time functioning is necessary. Now, how the time management is done within the real-time operating system? So it is done by using something called as high resolution real-time clock, RTC, which is an hardware chip which is found inside the embedded system. And this hardware timer is programmed to interrupt the processor or the controller at fixed rate. Now, and that interrupt, timer interrupt, we call it as timer tick. So, timer tick interval may vary. It depends on the hardware timer. So usually it will be in terms of microseconds. That means for every few microseconds the CPU will be interrupted. So I have the example here. Say I have a system time is updated based on the timer tick. Now to update the system time, the system time all of you would be knowing, so the bottom right corner you get the system time. I want this system time to be updated based on the timer tick. Now say system timer is a 32-bit wide register. It has a 32-bit wide register, and the timer tick interval is say 1 microseconds. Now the system register will reset in approximately 1.19 hours. Say how? Because I'm assuming it's a 32-bit register, 2 raised to 32 into, I'm saying the timer tick operates in the interval 1 microseconds, 2 raised to 32 into 10 raised to 6. Why 10 raised to minus 6? Because microseconds range. So divided by 24 hours into 60 minutes into 60 seconds, approximately it is equal to 0.04 days. I convert it into hours, I get it as 1.19 hours. That means, so this system time register, which is a 32-bit wide register, every 1.19 hours it will be reset. And similarly, if I assume my timer tick is operates at the interval 1 millisecond, so then 2 raised to 32 into 10 raised to minus 3, so 24 hours into 60 minutes into 60 seconds is equal to 49.7 days, or approximately you can say 50 days. So this register, which is a 32-bit system time register, 32-bit register, it will be reset once in 50 days. Now